This is lab number 9, implementation of analog PID controller. Well, in this lab we will use the servo fundamental trainer. From the basic control theory, it is evident that the PID controller can improve the steady state error of the response. Similarly, we are having the PID controller, it can improve the transient response of the response. Similarly, PID controller, which consists of the proportional term plus the integrator plus the derivative term, that can improve the overall response, that can give the best response. So here is how we can see the proportional term. Proportional term is simply operation amplifier. This is the operation amplifier, and this is the analog implementation of the PID controller. So that's why we will use the operation amplifier here. This is the operation amplifier, and this operation amplifier is used as a simple gain controller, as a variable gain controller. Here at the input, here this is the resistor R1, and the feedback we are having the resistor RF. And the gain, voltage gain of this op amp, that is equal to RF divided by R1. So if we can, we are having the feedback resistance is equal to 100 kilo ohm, and the input resistance is also 100 kilo ohm. So the value will be, the voltage gain will be equal to 1. Similarly, for RF resistor, the value of the RF resistor is 10,000 kilo ohm. So the voltage gain will be 10 times. Okay, this is the operation amplifier differentiator, in which the capacitor is in the input and we are having this resistance at the feedback. This is operation amplifier differentiator. It can differentiate the error signal. Similarly, we are having the operation amplifier integrator, in which the capacitor is in the feedback and we are having this resistance at the input. This is the block diagram of the this lab. At the input, this is the square wave. The square wave will be applied to the motor. Right? This is the square wave motor, and this square wave will be applied to the operational amplifier summer. So here in this case, the operational amplifier will be used, and that operational amplifier will be used as a summer. So operational amplifier can perform two tasks. One, it can be used as a variable gain controller, and the second, it can be used as a summer in the analog control system. Right. So we are having this different signal. This is the error signal, and this is the PID controller. So we are having here, this is the differentiator part. This is the Kd term. This is the Kd. This is the potentiometer where we can achieve the value of the Kd term. Similarly, this is the proportional term here, and this is the integrator. So the error will be integrated here. All the values of P, the derivative terms, and the integrated terms will be added here. This is another summer. And if we can increase the value of the gain, so we will require another operation amplifier, and that operation amplifier will increase the gain of this error. And that error will be further applied to the DC motor, and that will be the output shaft of the DC motor. So the output shaft, the position of the output shaft here, that will be the theta naught, and this theta naught will be given by the output potentiometer. So here we will having at the input at the summer both the position of the input signal, that is theta I, and the position of the shaft, that is applied to this is theta naught. So this will be the response, theta naught will be the response of the DC motor, and that is the input square wave. So we will give square wave to the DC motor, and similarly we will check out the response of the DC motor here. Here how it looks like on the trainer. The first part here, there is a square wave here, Here is a triangular wave over here. Similarly, we are having a DC input, positive DC 10 volt and negative DC volt. So in this case, we will apply square wave of amplitude 10 volt over here, and this potentiometer is used to increase or decrease the amplitude of this square wave. Similarly, the output of this wave that will be provided to the summer, and in this case operational amplifier is used as a summer. So this is the output will be applied to here to this op-amp, and this op-amp is used as a summer. The output of this op-amp will be applied to this gain controller. So here we can also increase or decrease the gain, and similarly the output of this P1, this potentiometer, can be further provided to this buffer. Here this is the controller part. The upper, that is, we are having this capacitor at the input, and we are having similar resistor over here and a resistor at the output or at the output. So this is the differentiator circuit. This is the differentiator circuit. Below here, this is the proportional controller. At the feedback, the value of the resistance is 200 kilo ohm. At the input, the value of the resistor is 200 kilo ohm. So the gain of this proportional term will be 1. Similarly, this is the integrator circuit, where there is a resistor at the input. This is the resistor at the input. This is the inverting amplifier, and we will connect this here to this capacitor, and that will become integrator circuit. And this, the output of all combined, these three will be here. We can also increase the gain, which is evident in the block diagram, and the output of this PID controller can be provided to the DC motor. So this is how it looks. This is the DC motor. This is the mechanical part, and this is the analog part.